Hello and welcome to the fifth part of the tutorial series for the COVID-19 simulator developed as part of the EUVABECO project. In this scenario, we simulate the wave of infections with virus variant Delta in Greece. We compare a baseline scenario without any changes to a counterfactual scenario in which variant Delta emerges earlier in time. First, the baseline simulation is performed by clicking the Simulate button. After a short simulation run, the results are displayed. The Save button is then selected to save this scenario under the name Baseline. For the first counterfactual simulation, click the Scenarios button with the cogwheel icon. This opens 3 selection areas below the date settings. In the right-hand selection area, the Variant Modifications section is displayed. The variant Delta is selected. The emergence of the variant is shifted 50 days earlier. All other settings remain unchanged. Click Simulate again. Once the results are displayed, this scenario is saved under the name Delta 50 days earlier. After completing these steps, 2 simulations are available. Under the heading Simulation Results, the scenarios are compared. Using Compare and Add Comparison, both scenarios are displayed side by side. When looking at the results, clear differences become visible. When the variant emerges 50 days earlier, the number of infections increases substantially. The resulting wave is considerably larger than in the baseline scenario because the variant coincides with a period of lower population immunity. At the same time, variant Delta caused more severe disease than the later Omicron variant. As a result, substantially more hospitalizations occur. Notably, an extremely high peak of infections appears during 2022. These results imply 2 things. First, if a highly transmissible virus variant emerges during a time of low population immunity, specifically before the full rollout of the vaccination campaign, more infections and severe cases occur. Second, however, these simulations also highlight the limitations of the model. Setting scenario changes far in the past while simultaneously simulating up to the end of the pandemic leads to unrealistic results. The reason is that real-world conditions change significantly over long periods. These changes are due to virus variants, immunity, human behavior, risk perception, and testing practices. Our scenario alters the trajectory of variant Delta, but the model continues to assume that the underlying dynamics remain comparable. This introduces substantial bias in predictions far into the future. For example, the vast increase in infections in July 2021 would in reality have triggered the implementation of countermeasures. Additionally, the model assumes lasting immunity following infection. The sole exception is Omicron reinfections among individuals previously recovered from wild-type, Alpha, or Delta. In scenarios generating very high cumulative infection numbers, the susceptible population may become depleted, causing an artificial extinction of transmission. Therefore, long-running simulations can become misleading. Further limitations include the fixed demographic and testing covariates. In the simulator, age and sex distributions of cases remain at their historically observed values, regardless of the simulated scenario. Since these covariates influence progression to hospitalization and death, the model implicitly assumes an unchanged demographic composition of infections. Additionally, testing volumes and test positivity rates remain unchanged. In practice, changes in infection incidence would affect either testing number or test positive rates or both.